In this video, we'll see the half adder and full adder logic circuits. First, we'll start with the binary addition and sum and carry definitions, and then use logic gates in order to implement these adder circuits. Let's start with the most basic arithmetic operation, addition of two binary bits. You can see that 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 1, 0. Here, we are going to get this most significant bit as the carry. Now let's see two definitions. First one is the half adder. It's a combinational circuit that performs the addition of 2 bits. And full adder is a combinational circuit that performs the addition of 3 bits, which are 2 significant bits and a carry. And two half adders can be used to create a full adder. Now let's see the half adder. This is the truth table for the half adder. You can see that we have x, y, the carry, and the sum columns here. And we have all possible combinations for x and y, 0, 0, 0, 1, 1, 0, and 1, 1. So if you would like to figure out the functions for s and carry, let's see for s first. Here we have the value as 1, so we can write this row as x complement and y. And here we have x, y complement. So if we add these two minterms, we are going to get the function for s, which can be seen right here. And for carry, we only have a single one right here, and we can write x, y is equal to carry, and you can see it right here. However, if you look at the definition of the sum function, you can easily see that this is an XOR operation between x and y. As we said previously, s is equal to x or y, and carry is equal to x and y. Now let's see how we are going to implement this half adder with logic gates. For this first sum of products expressions, we can implement our circuit as seen on this figure. Here we have x complement y ORed with xy complement. So this is x and y complement, x complement and y. Together these are ORed, and the result is s. And for carry we only have a simple AND gate here. However, if it's possible to use an XOR gate, we will be able to implement this circuit with only 2 gates. You can see that the sum is equal to x XOR y, and the carry is equal to x and y. So while we have 4 gates on the left-hand side, we have only 2 gates in the circuit on the right-hand side. Now let's take a look at the full adder. Here we can see the truth table for the full adder with the carry and sum at the right-hand side. And these are the terms that are obtained from the truth table. Let's write the expressions for sum and carry. First, for the sum, we can write, we have x complement here, y complement, and z, which is this term. And we are going to have x complement, y, z complement, which is this term. We will have x, y complement, z complement. And finally, we are going to have x, y, and z. And let's see for carry. For carry, we are going to have x complement, y, z, this term. We are going to have x, y complement, z, this term. X, y, z complement. And finally, again, x, y, z. And you can simplify the carries equation as xy plus xz plus yz. You can use the k-maps method for this. Now let's draw the logic circuits for these two functions. First, let's do it for the sum. So we will have 4 AND gates because we are going to have 4 terms. And these are going to be ORed to get the output. So this one will be X complement, Y complement, Z. This one is going to be X complement, Y, Z complement. This one is going to be X, Y complement, Z complement. And this one is going to be X, Y, and Z. And they will all be going to the OR gate. And this is going to be our output, which is the sum. And for the carry, we are going to have 3 AND gates. And finally, we are going to have an OR gate. This one is going to get X and Y as the inputs. This one, X and Z. This one, Y and Z. And they will again go to the OR gate to give the output carry. But we can implement the full adder with 2 half adders. This is first one, this is the second one, and then OR gate. So let's see the inputs and the connections between these gates. So we will have X and Y XORed in this gate. And we will again have X and Y ANDed at this gate. This output is going to be connected to the second XOR. And we will have the carry input Z is going to be connected to the second XOR as well. And this is going to be our sum. And we will have this X XOR Y as an input to the second AND gate, and carry in as another input to the second AND gate. We will have the X and Y to be connected to the OR gate at the output. And finally, we are going to get X XOR Y ANDed with Z here, which is going to be connected to the OR at the output. And this is going to be our carry, which is X XOR Y ANDed by Z ORed by XY. And our sum is equal to X XOR Y XOR Z. This is our sum, and X XOR Y ANDed by Z ORed by XY is equal to the carry. This was the end of the video. I hope it's been useful for you. If you have any questions or comments, please write them in the comment section. Thank you for watching, and see you in another video.